Hello everybody. In this video we're going to tackle a problem that has to do with friction. So we're given the image here that I've drawn, and that is at least supposed to be a dresser, and it has the dimensions shown in the picture. So let's tackle the problem. So part A says if the dresser is sliding with a constant velocity of f that I've drawn on the left side of the picture here, maybe I'll show it in red to be a force. The magnitude of the force, to find F, the magnitude of the force that the person applies. All right, so our goal is to find F in terms of the other variables. So just going over them real quick, we have the height of the dresser, we have the length of the dresser up top, and then we have the normal force exerted on each of the two legs of the dresser, assuming we have a 2D dresser, right? And then we have the height, little h, from the bottom of the leg up to the force. All right, and then part A, we need to find the magnitude of that force. So we can start, I suppose, by drawing a free body diagram, perhaps that box there. So we have this force here, the normal force in P, this here, the normal force of Q, and we have the force that we're looking for there. All right, and then there's going to be some friction in this problem. So the friction will be opposing the motion. So it's going to be to the left there. And I'll denote that with force of F, so force of friction. And then they also tell us for mu of K to use mu of K for that friction coefficient. All right. That is almost a complete free body diagram. Just need to add the weight there, just like that. So now it's just a matter of summing the forces. So I'll begin by summing the forces in the y direction. Sum the forces in the y. And what do we have? Well, going up is NP plus NQ, and then going down is the weight, so W. All right, easy enough. And then we're going to sum the forces. Sum the forces in the x direction. In the x direction, so going right, we have F, and going left, we have that force of friction, just like that. So then I can say force equals the force of friction. And then we know, of course, that the force of friction is just equal to the normal times mu K. Alrighty, where the normal can be written as NP, so normal equals NP plus NQ, and that's actually going to equal the weight, right? Or in terms of the variables given, it's going to equal mg. All right, so let's first rewrite force equals mu K times the normal. So force equals mu K times mg. And there you have it. We found the force in terms of the mu K and mg. And that, of course, will have some units not specified. Let's just say that they're newtons. All right, that's part A. Then we have part B. Part B says, find NP, the magnitude of the normal force, as shown in the figure. The legs are separated by a distance L, as I've shown. And it says express your answer in terms of m, g, l, h, and mu k. All right, well that sounds doable, I suppose. We've already done some of the work. So where to start? So we have the equation we already wrote, so we can write NP, and we could say that's equal to the weight minus NQ. All right. So we know that weight is mass times acceleration, in this case gravity, so minus mg, and then we just have to determine what NQ is. So I think we're going to want to introduce a couple more equations in here. And so we have our two force equations, but we also can add a moment in there, so we can sum the moments. So if I do a sum of the moments, and at what point should we do it at? Let's do it at NP, or yeah, let's do it at NP, or yes, NP. And the sum of the moments is going to equal 0. So then we have NQ times L, the distance there, and that's going to be going around like that in a clockwise direction. Therefore, that's going to be negative. And then for that force that has a distance or height h, little h, it's going to be, and that's also in a clockwise direction, so it's going to be negative fh, like that. And what else? And we have the weight there, so the weight is going to be also in that negative direction, because it's going down, so it's going around like that. Or actually, I was wrong about the first one, wasn't I? Because this is going up. That's going up, so that's actually going to be counterclockwise. So sorry about that. So that's actually going to be positive. But then the weight, W there, times half of L. So weight times L over 2. Alrighty. That looks about right, I'd say. So then solving this for NQ, what do we get? So I can say NQ L equals FH minus WL over 2. And I'll actually rewrite that as MGL. And if I divide everything by L, the whole expression here, those L's cancel, and we get something that looks like that. All right, we're getting there. So if we plug in that NQ into the first equation there, we get NP, what we're looking for, is equal to mg minus fh over L minus mg over 2, like that. And then a couple things. First off, we could put a 2 there, right? 2 over 2. So if we do that divided by this mg over here, we're going to get a positive 1/2. So 1/2 mg minus h over L. And then the force, we said from the first part, is equal to mu k mg, just like that. All right, and I believe believe that is our answer. So let's rewrite it a little bit nicer here. mg over 2 minus mgh mu k over L. And there you go. And then we'll perhaps just for giggles say that the units for that are in newtons. All right, not too bad so far. Then part C of the question, part C, says find NQ, the magnitude of the normal force as shown in the figure. The legs are separated by a distance of L. So it's the same as before, except we're looking for the other leg. All right, well that shouldn't be too difficult, I don't think. So let's write that first line there on B, right? So NP equals mg minus NQ. So this time, go down to give us some room. This time we're solving for NQ. So I can say NQ equals mg minus NP, like that. And we just said from the previous problem right above, right there, that NP, let's plug our answer in there. So mg over 2 minus mgh mu k over L. So if we distribute that negative, I'll just get rid of the brackets here. Negative there, negative and a negative is that positive there. So then we get NQ is equal to, so again, put a 2 there and a 2 there. 2 minus 1 is mg over 2 plus mgh mu k over L. So it looks like the only difference between NP and NQ is that one is adding the second term and one is when you subtract the second term. Alrighty, not too bad. Alright guys, now for part D. I took the liberty to bring this image down and to give us a way to take the moment a little bit easier. So what does part D say? Part D says find h max, little h max, the maximum height at which the person can push the dresser without causing it to topple over. So this is a tipping problem, and generally when you have a tipping problem, you want to take the moment about the part or the leg or whatever the problem has, the very edge piece that it's tipping over. So had the force been on this left side, we would have done the moment about NP. And likewise, had it have been a box that doesn't have legs, we would have redrawn the free body diagram to show that normal force on the far right, and that's what we would take the moment about. So let us jump right in. So the sum of the moments about N and Q is going to be equal to, well, we could say the mass first, and that's going counterclockwise, therefore it's positive. So mass times L over 2. All right, and then that force there, it looks like it's a distance height away, and it's going clockwise. Therefore, it's going to be negative, so minus force times that height. And then the other force is NP, but we're looking at the moment where it's tipping. So when it's tipping, NP, that's when NP is actually equal to 0. So NP is 0, so I'm not even going to waste my time writing it. So that's sort of the key to that problem, I suppose. And once you know that, it's just a matter of plugging everything in. So force, I'll just go ahead and write force and height. And then when I solve for height, I get ml over 2 times the force. And I think we will rightfully recall we solved for force in this first part, and it was mu k mg. So 2 mu k mg, like that. It appears that the m's cancel out nicely there. And then that means that height is equal to L over 2 mu k g. Something tells me that I did something wrong. What did I do wrong, y'all? No feedback? I know I did something wrong. I must have. This expression looks correct. 2 divided by that force. Oh, of course, I put mass instead of weight. Yes. Weight, G's cancel. Bam. Sorry about that. So the maximum that h would be before it topples over is going to be defined by that expression there. And of course, it's in whatever units you're measuring in. And I guess I'll humor y'all and put an m to stay consistent with my odd units I've been using. Well, there you have it. The reason that is the moment when it tips is because that's when we're setting n to 0 at that point. And when n is 0, that is the moment that tips. And there you have it. That's how you find them in terms of variables. It's not too bad. There's not a super systematic way that we go about solving these. Really, you just remember that you have your 2 force equations, and then you can take the moment about several different locations. And I'm sure just the process of playing around with it in 15 minutes ought to be enough to make sense of the problem. So I hope this was helpful in some way, and I hope someone out there finds it useful. And I will certainly catch y'all in the next one.